My name is Hafiz Sheikh, and I'm the business head for Manufacturing Today India magazine. On behalf of ITP Media, Manufacturing Today, and Husky Injection Molding Systems, ladies and gentlemen, in today's webinar on a very interesting topic, which is unlocking the potential of polycarbonate, best practices for successful injection molding. Let me introduce my organization. ITP Media publishes more than 80 plus magazine globally. ITP Media Group reaches an audience of more than 104.6 million people globally through its leading brands, websites, social media platform, and events. Our portfolio includes magazine for hospitality, architect, manufacturing, construction, healthcare, media and broadcast, and many more. The platform which we are hosting today is Manufacturing Today, which is India's leading magazine, which focuses on people, process, and technology for SME and large manufacturing organization. Let me also introduce our partner for today, Husky Injection Molding. Husky Technology is the leading industry technology supplier to the plastic processing, design, manufactures, and service the industry's most comprehensive range of injection molding equipment, includes machines, mold, hot runners, auxiliaries, and integrated system. Customers use Husky's equipments and services to produce a wide range of for many industries. Husky supports customer in overall 100 plus countries, and it has manufacturing facilities located in Canada, United States, Luxembourg, Australia, Switzerland, China, India, and Cruise Republic. We have a very eminent speaker to him last time, Mr. Balaji Mulur. He is the business manager for hot runners and controllers as Husky Technology. Let me introduce him again. This time, he is responsible for hot runners and control sales for Asia South and Australia and New Zealand. Mr. Balaji is based in Singapore. He has experience of more than 31 years, having graduated from NTTF as tool and die makers with mold machine background. He is with Husky since 2005, started as service engineer and currently as business manager. Balaji, welcome, and over to you for your enlightenment and knowledgeable session.
Thank you very much, Hafiz Sheikh, for the introduction. Hello, everyone. So first and foremost thing, thank you so much for attending this webinar for polycarbonate. Polycarbonate is basically a very interesting material that we are using on modern applications we touch on everyday lives. The best example would be a mobile phone. Why? Because in a mobile phone, we have some of the components that are using polycarbonates, which are kind of flexible in its own ways. So I would like to present about topics today for the webinar. That would be about our Husky technologies. Hafiz has already mentioned some of them, but I'll go a little bit in depth on it. And that would be understanding polycarbonate itself, like how exactly this is going to be done. And injection molding work cell influences, meaning to say that how we exactly treat polycarbonate as a resin. And then we have a hot runner design influences, why it is so important to have a good hot runner. Then eventually, we are going to talk about injection molding, process troubleshooting, which is a key for this particular webinar itself. Let me go with Husky, like who we are and what we do. Like Hafiz already mentioned, we are injection molding company, leader in equipment and services. We also are leaders in hot runners and controllers, mold makers that we supply for converters and as well as brand owners. We have a standardized engineering and manufacturing processes to ensure consistent performance of our systems. We also have a highest quality and most reliable material delivery systems and controllers with the shortest time to the market. So this puts us in a kind of a leadership role when we are working on it. Husky has a global network. First and foremost thing with respect to manufacturing. We are headquartered in Canada, just about away from Toronto. So we have manufacturing facilities in the United States, Luxembourg, India, China, and Switzerland. We also have spare parts centers globally that you are seeing on the highlighted on the screens, that having it just to making sure that we deliver our spare parts at the fastest pace possible. And we have technical centers to support them as well. And service and sales officers are very critical for the market today to making sure that we support the customers who are running the productions for any issues that are going to be supported when it comes to service, as well as sales for any new requirements. And finally, we have refurbishment and conversions, which I'm going to speak on that one as well in my next slide. When it comes to hot runners that Husky is going to supply, we always prefer to start with a product that is going with prototyping, that's going with a single drop. So when we have a single drop, this will kind of test what are the kinds of problems that we may face when we are going to design for the plastic part that is going to come to us. So once we have that, it's been tested on a single drop, we go for a low cavitation. Low cavitation can be a 2-drop or a 4, for example, purely because to understand how exactly that this is going to flow when it comes into the manifold, and especially for balancing the hot runner system. And then with all these things, we run through an MPI, which also I'm going to talk about more on the future slides, of high cavitation, but more confidence that it'll all be good using a single drop, using with low cavitation, we're pretty much carried to develop a high cavitation as well. And then we also have stack systems. So these stack systems are pretty unique. If you have a higher tonnage machine and also with a bigger shut height, you can able to incorporate stack systems to making sure that you can produce twice the amount of parts for the same cycle time. This is advantages that Husky can able to do that. When it comes to hot runner kinds of systems that we have, you have a unique one that called as angled manifold system. What is this? Angled manifold systems are basically designed for a kind of a contoured plastic gate position, where usually it is going for automobile lenses. We have drop-in systems that is already been built completely. All we have to do is to install them with a plate which is already manufactured. It is flexible to go to any kinds of pitching and dimensions that's adaptable. We have side gate nozzles. So what does this side gate do? Side gates are basically for medical components products that's going for pipettes or lures. And then we have something called ultra short injection control. The ultra short injection control is a very unique system today that you don't see anywhere except Husky in the market. Why? Because there is something called this mold the unmoldable. In other words, if you cannot able to produce a part in a conventional injection molding, which has a maximum amount of peak pressure, Husky can able to take this responsibility to making sure it can be done with an ultra short injection, which can be also discussed a little bit. We have a separate webinar for that, but I can also touch base on that during the next slides. Temperature controller. This is very, very important when we have a communication between hot runners, that is the mold hot runners versus the controller. If we do not have a good temperature sensing capabilities between mold and controller, we may end up having not producing good parts, purely because the communication between controller and hot runner is very critical, thus by producing good products over time. In hot runners controllers, in Altanium series, we also have UltraSync E, that's for valve stem motions for the system. We have ISCVG for timing, and also a sequential controller called VGS. So what does this sequential control do? Many of us know it's basically anywhere for a product which will have multiple gates. And if you want to fill the part in a sequencing situations, that is where sequential come into picture, that Husky can able to be selling as well. And there is something unique that Husky is going to sell. That is Alsanic sequential control for mold action servo control. What is this? For any of the sliders, cold decks for the cold system that you have, the sliders that you're going to incorporate, Husky can able to make this control with a servo driven, which will be more accurate of positioning, so that you can avoid many of the problems that comes on and as well as those. And then we have ultra short again that I'm showing it to you, that will be having with the mold and controller coming together with Husky. That's I said that ultra short is something that mold unmoldable. So we work very closely with the mold makers and stakeholders like OEMs to making sure that that happens. Finally, I would like to touch base on refurbishment and conversions. So in the event of a problems that in a particular number of drops, let's say 64 drops, for example. Some of the drops are not working for whatever reason, and if your output is completely reduced, Husky takes pride in making sure that we take back the systems, we refurbish completely, and bring it back to life on 100% production. So we also make sure that we have on-site training and repairs. Why? Because there is a kind of a situation where person who is responsible for taking care of our hot runner systems can be moved to another place, or a new guy representing the organization may not be aware of our product. So we ensure that time and time again, we visit our stakeholders to asking them if they need to be training, and we really provide them, making sure that they are up and running in a better way. Call desk and the technical support. These are for spare parts ordering as well as draw required. We have dedicated call center systems globally. And e-commerce, Pronto Direct. These are the ones which can be ordered directly online for lower cavitation purpose and Pronto systems. Pronto systems is nothing but we have a dedicated pitch, and if that falls within the framework of that one, it can be ordered faster and can be delivered as well. Now we are coming to the important topic of polycarbonate application introduction. Polycarbonate, as we all know, is a plastic or unique and very interesting material. We have so many plastic. Why polycarbonate? This comes into, I will be showing into the slide, is that because it helps us in many ways compared to other materials that we have it today. In the past, we used to have glass. We used to have products with metal. We used to have products with ceramic and wood as well. But why we choose plastic? It's because it's unique in combination of properties. It's a very rigid and also tough. It is electrical resistant. And there are so many advantages of plastic compared to other ones. So in a way that I would say that when you come across here, the difference that we are going to have is because it is so unique, low weight per volume, strength to weight ratio is different, material property customization, impact resistance, manufacturability, and finally, it also is having electric resistance as well. So in a way, we can able to see that polycarbonate has a lot of advantages using them compared to other products like glass, metal. In every application has its needs. Every material has its strengths, as well as to making sure that this is sustainable in a circular economy. Now let me go into a little bit of history of polycarbonate. I'm told based on some of the studies that we have made, it was kind of in the 1890s, there was a kind of development started for this polycarbonate resin, but nothing happened, more so in a laboratory in Germany. But over time, it starts to kick off somewhere in the 1950s, again in Germany. It was a kind of, they developed something called as a linear polycarbonate. At the same time, after a week or later, United States came up with branched polycarbonate. So these two together, they worked on, and some of them patented of some of the critical brands that they are today, marketed well. And during that time, it did help for having a kind of, compared to glass, it did work well for its clarity, toughness, and so on. And until such time, it's further history today, what we are seeing polycarbonate on a many more wider scale. Coming back to polycarbonate, where and all polycarbonate are basically being used. We use it in blow molding, we use it in extrusion, we use it in thermoforming, we use it 3D printing, and finally we use it in injection molding. That is what is key to us for the rest of the is also important, but our focus is on injection molding. So in a given market that we have for polycarbonates to sell, we have extensively used this one for eyeglasses. In the past, like olden age, most of the eyeglasses were to be used in glass. But over time, as in polycarbonate became easy to use because it's lightweight, toughness, clarity, everything changed to eyeglasses for eye protection. And the other one is the automotive and lighting lenses. Device housing, especially for medical and consumer electronics as well, as I mentioned, like phones, mobile phones, fluid management, medical tubing connectors, internal operating assemblies, media storage, DVDs, CDs, we name it, everything goes into polycarbonate today. Why we are going to have a key material advantage for this high transmission is because of its toughness that I already showed you with the other slides before. The impact resistance, also a heat, it has been put up again and again to making sure that the importance of polycarbonate itself. And we also can able to blend with additives, alloys, and also for coatings. So this one will be helping in a way for us to making sure that the several devices for medical and consumer electronics utilize polycarbonate for exterior housing and integrate assembly operations. And then on, I would like to touch base on, since we had glass, it also has a great clarity. Why did we go with polycarbonate? It's only because that it has been tested and proven that polycarbonate has a 7 times clearer clarity compared to the glass. It could be astonishing sometimes, but this is what the study says. And again, it goes into lightweight. And many of the polycarbonate applications are related to its clarity, and it is used for windscreens that we see in our cars. And also it is used in light transportation as well as aerospace. So in a way, I can say that the clarity and transparency also contributes for medical diagnostics, equipment and confirmation, breakage and safety patterns. So it's a formability. Formability to say that it can be formed into any shape, because the advantage that we have for polycarbonates. So now we have something called as blends and alloys for customization. So what are they? Polycarbonates are kind of able to blend the resin to PBT and PET as well, and amorphous resins like ABS and PMMA, and also the resins that are kind of high temperature resins like PSU and PEI. We also have fillers and reinforcements. What are these? It can be filled with glass and carbon fibers to strengthen the material of polycarbonate. And we are able to have it to use the colorants, visual effects, and also additives can be used to performance to improve the ultraviolet stability, weatherability, or flame resistance as such. Just to go with the chemistry of polycarbonate itself, first and foremost thing we have to understand, or we all know that thermoplastic itself, the polycarbonate itself is thermoplastic. And due to its amorphous structure, it can be heat applied to soften the material to a semi-liquid state. When that heat is removed, it forms a solid that becomes cold. So whenever that the heat is applied, it softens. When heat is removed, it solidifies, and vice versa. It can be done in multiple ways, meaning we can able to recycle them if we do it properly. And also, polycarbonate has a high glass transition temperature. What is this? Sometimes we call it as TG. So TG, in a high glass temperature, transition temperature, it's about 147 degree centigrade. And at about 155 degrees centigrade, it tends to flow at about 155 degrees C. So usually the polycarbonate processing temperature that we can able to do it at, it's about 290 degrees centigrade to 300 degrees. So this is something we call it as a strong backbone. What is this? As far as the chemistry is concerned, it's a pretty strong backbone. Unlike polyolefins, with a backbone of straight carbon polycarbonate, and is made up of oxygen and benzene rings. That they are, we see 000C or OOO and C, and we have the 3 rings here. These are basically to having the benzene rings inside. So these two together structures into to making to carbons and hydrogens, giving us the much higher molecular weight to making sure that the polycarbonate are basically the best ones to be used. So this also gives material some polarity, making it a kind of hygroscopic or capable of absorbing moisture, which I will be explaining on the next slides as well. Influences on its properties. Clarity. What is this? Clarity seems to be a situation where we may say, oh, it's very clear. In other words, it is not. It's very easy to identify any kind of a problems that may see on a polycarbonate plastics, meaning to say that we can see black specks, for example, if the clarity of the resin is turned off kind of yellowish for whatever reason, that can be seen as well. These are the things that influences chemistry. So chemistry refers to melt viscosity. What is this? Melt viscosity, we need to make sure that the resin is homogeneously mixed and the flow should be proper. The residence time of the resin should not take too long to be staying it so that it tends to change its properties and goes into next is thermal sensitivity. Thermal sensitivity is very much related to temperature. We need to make sure that we are not going to rise up the temperature too high to degrade this resin. That's another thing. And lastly, hygroscopic. I just mentioned in my previous slide, hygroscopic is something that which is having absorption of water. So any polycarbonate, it is just going to absorb the water because of the reasons that I'm going to put up to you on my slides. We talked about injection molding work cells. Work cells is pretty much reflecting to you on the screen here. We start with the resin. That's the key thing that for us. So when we have a resin, how do we handle it? We need to make sure that polycarbonate is well dried, enough dried to making sure even excessive drying also causes problems. So enough drying to making sure that it's within the dew point. And then we are going to have it in the resin that is going to be filled up into the feed throat. Then eventually it goes to the melt, injection carriage and barrel. So this injection and barrel is also key to making sure that we have enough and correct residence time of the resin. And then you push the plastic into the hot runner. And this also lies a very critical part that, as I said in the past, that Husky is going to work with stakeholders to understand the behavior of the part as well as the resin with running low cavitation and multiplied into higher cavitations. That's why hot runner design is very important as well. And then we go with mold, cavity and pores to making sure that these are kind of done with very well. Air ventings, the design, the gate positions, these are all the key on the mold point of view. And finally, talk about machine clamp tonnage. If we do not have any machine tonnage, it's always kind of law. For every reaction, there is always opposite reaction as well. Action and opposite reaction. That comes to where is that due to the injection pressure that's going to apply from the plastic, if you do not have enough clamp tonnage, the mold tends to open up, causing flash and also uneven fillings. So that's why clamp is very important as well. So here we are showing about all the things that how exactly this is going to show. These are critical, about 5 to 6 of them. And eventually that we are going to go for the next slide, the work cell category for the resin itself. Polycarbonate, again and again, I'm going to repeat that has its own challenges to mold, with a reputation being highly viscous. If you plan to mold a polycarbonate part, it's most likely to be pressure limited and require high skill processing, purely because it's being an amorphous material. Polycarbonate viscosity will decrease as temperature set point increases. So let me put it this way. If I see that the peak pressure is going up during any kind of a processing time, what generally the people will do is to go with increasing the temperatures to make, obviously, when we increase the temperature, the viscosity changes to having easy to flow. But is it the right thing to do? That's exactly that we are talking about work category resins here. So we need to mention, if we're going to happen to increase the temperature, the material is going to degrade, but you will get a part, but it's not something which will be usable. That also has problems, structural defects eventually, when it comes to having it because of higher temperatures that we are going to set up on the controller or a barrel or whatever it is. So that is something that, especially for the medical grades, we have to ensure that we cannot afford to have kind of what you see on the screens here, that yellowish, that is burn mark, purely because we need to having within the specification cycle and the pressure limitations and avoid discoloration. These are key for us. And now we talk about moisture. This is again hygroscopic, why it is so important to making sure that we are not going to have any kind of moisture into plastic resins. The molecular polarity of the polycarbonate that having that is itself is hygroscopic material. This means it absorbs moisture even from the ambient air. In normal conditions, if we keep a gaylord of plastic and leave it, polycarbonate easily absorbs the moisture. That sensitive is the resin itself, as we all know. And we need to make sure that each time that this particular batch of resins that is being kept outside or inside due to humidity factor, shipments from one container to other when it's coming from overseas, this is to make sure that we are going to have a right amount of drying time, temperature set to remove that moisture that is hygroscopic in nature itself. Undried the moisture can show cosmetic problems. And not only that, it also has structural defects because it tends to crack over time after it is molded, which may not see now, but later part of it. That's why I always making sure that we from Husky to ensure that our people that we are making this webinar, how important drying of PC material itself is all about. And also we need to make sure that the material that runs through the mold, we will not have any kind of water leaks. That's also critical. We may end up having a good amount of moisture removed from the resin and conveys to the barrel, screw, and hot runner. But eventually it backs to square one if we have some leaks of water because during the time of injection, it drops into it, then there are problems as well. It is that sensitive. You're kind of seeing some long lines here. This is the illustration of basically the polymer chains, which comprise polycarbonate at a very molecular level. These are very long lines because polymers are long molecules, has greater length of these molecules, give polycarbonate its strengths. But these chains can able to have problems with a very bulky, because the longer the chain, the bulkier it becomes. And if once it's bulky, again, it relates to difficult to flow. So when it's having difficult to flow, so that what we have now is that, as I said, the polycarbonate has an advantage to absorb moisture. Water comes into picture. Once the water comes into picture, it kinds of blends into these long chains and the molten state, and the moisture attacks these chains. Once it attacks, it tends to break. So once it tends to break this chain, we will have smaller polymer chains now, wherein it becomes less bulky, and in turn, the moisture kind of later on will be removed by means of drying, and then it will be easy to flow the plastic. That's how it all works. We are basically blessed by kind of how exactly the water also helps in breaking the polymer chain as well. But the dryer is helping remove that one eventually to mold later on. Now comes the critical part of our machine. We talked about resin, we talked about drying, and we now talk about the machine. Machine comes with the critical part of the screw and the barrel. We all know that the injection screw represents to having the material shear rate of up to 70% of it itself, around there. Another 30% will be maintained by the heats of the heat. We're giving external heat onto the barrel that transfers into melting it or maintains it. So out of the screw, we are basically divided into three categories. They will be feed throat, transition zone, and the meeting zone. So out of these three, we have to ensure that we all know that the transition zone has the maximum shear that's going to melt the plastic. So in the transition zone, and also the whole complete screw, we need to make sure that we don't have any kind of buildup of foreign particles or any solidified resin that is been stuck. And most importantly, also as well, the check ring is not kind of damaged. It should be maintained well. So if any of these problems is not done well, we can mold a part, but we end up with some problems with respect to stagnation, comparatively high melt viscosity because it's going to slip, and eventually smooth thermal profile will not be happening. So we need to make sure that the screw is very important and the barrel both are pretty much clean and neat to have a right amount of barrel and screws. Now we come up the clamp system. So to the poly units viscosity. The clamp unit tonnage are necessary to keep the mold half while the cavity fills. As I said, it's a Newton's law. When the injection is going to happen, the clamp should be maintained at the same time, the pressure that's applied. If we do not have enough clamp up from the machine that's going to support, the mold is going to buckle or going to try to open, which will cause innumerable number of problems that we may not be able to produce a good part. So it's also important to making sure that it has the kind of fit between tie bars. If we are going to increase above the tie bars, there is a problem as well. So there is a reason for that, to making sure that within the tie bar itself, to the mold should be molded for a specific part. So now, at any given time, we are talking about only the mold perspective here. When we have a product of a cavity of a shape, we need to make sure these are well vented. Generally, we make ventings as per requirements. That's one part of the trials that we are going to take. But how exactly the material flows to thing is depend on the process engineer, how he exactly sets the temperature of the polycarbonate after all the drying is completed. So we need to make sure that the drying is done by a dryer analyzer. That's critical to making sure that we will be going step by step, we are going no wrong. And then we remove heat from the melt, that is cooling, which is very critical to making sure that to achieve the cycle time that we have. And then we have access to removing the part, the ejection that we give onto all the places of position, so that it will not have stress on certain positions. And so giving the ejections of the part to release, it's very key. And then on, again, it starts from delivered melt from injection unit as well. It starts. Whenever we talk about the design of the system, so here again, it's mold related. We talk about the geometry of the product. So when we have a geometry of the product, the first thing we need to consider how much of amount of injection pressure that is there, because we have chosen the machine, we have chosen the hot runner supplier, and the one which is going to have is the mold now. And with the geometry of that, we talk about L over T. That's nothing but the length of the thickness of that one, and finally T refers to the thickness of it. L over T we call it. And then MFI. When it comes to MFI, that's melt flow index. If the melt flow index having a kind of, the higher the melt flow, the lower the viscosity, and vice versa. So those ones have to be taken into consideration when you are going to have a cavity and core design. That's the cold half. So we work closely with the mold maker to having virtual molding, or kind of to analyze a mold flow. We could call it as MPI. So in this one, we understand with the stakeholders to what kind of machines are they going to use, what kind of screw size that they're going to have, so how many cavities that they are going to use, and L over T, all these things on the left-hand side from the design. He takes over that and understands to have the viscosity with GT. We conduct a kind of virtual molding working with the mold maker. And then we have hot runners. So here you sign off a key thing that you see here: pressure constraints, melt system network design, thermal design, nozzle design, and gate design. This kinds of puts up into kind of a confusion. What is this happening? I'll just explain to you about this. Pressure constraints. We do not consider on a hot runner system with respect to pressure. For example, if we make a system of a melt channel smaller than the required size, obviously we will have pressure constraints. Once we have pressure constraints, we end up with peak pressure high and of course short shots, definitely. And then we have melt supply network design. So that's exactly, we need to go by equidistance. For example, if we have multiple cavities, in Husky, we have a kind of a very good product that we have anything of having multiple cavities, anything 2, 4, 8, 12, 16, 32, name it. We have equidistance, we have level changes, same diameter of melt channels, to making sure that our balancing are well done. So this is a very key advantage of going with Husky, making sure that we are pretty much guaranteeing on certain assets to having these balances are very important. That's exactly the melt supply network design. Thermal design. This is key as well when it comes to how exactly I'm going to profile the heater on the manifold and how many wattage of heater I'm going to use, what is the advantages. All these things would come into thermal design for us. We need to study that. And nozzle design. Nozzle design comes into what kind of nozzle series I'm going to use. Am I going to go with channels of how much it is, depending on the volume of the resin that is going to us, as well as the part weight. That's exactly that Husky is going to work on. And finally, gate design. How best is the gate design that I can position it is to run to MPI? If I were to run this gate to be positioned at this X place versus the other one which has been given, it would be better. We would work with the mold maker and the stakeholders as well for this, to making sure that all these things has to be considered for hot runner design. And now comes cavity count. So this cavity count is kind of arranged in a situation where how do we arrange the blocks of cavities and the number of drops and the pitching that we are going to have. We have certain minimum requirements of pitchings as well as we have arrangements of those, which I'm going to explain in these slides. Let's take 32 drop as an example. We have 32 is 2 times itself, 5 times, and the power of those, the 2 times 4, 2 times 8, 2 times 16, and 2 times 32. These numbers represent the splits or divisions to be having it to melt its way from the barrel to the cavity, and then on to use that number 4 to represent X division that I'm going to explain to you here. If you see the screen here on the top, both of them are 30 cavities or 32 drops. We have one line 2 times 16, and the other one is 4 times 8. Why do we design like this? It is because of how exactly the mold is to be attributed with respect to the product. We have kind of a slider, a particular product that comes into picture. Obviously, we cannot incorporate them into the green one that is 4 times 8. We have to go for 2 times 16. But if we have any of the smaller parts that is having, do not have sliders, we can always incorporate 4 times 8 to making sure that, because we can pull it up within the framework of the machine splittance. But here, even at 2 times 16, we can do that, but it will be going on a linear scale. And the same thing attributes to our 2 times 16 drops, for example, or 2 times 16 again here, to making sure that how exactly we are going to design the system. We have 2 types of design of hot runner melt channel. Either we can go with X or we can go with H. So what is the advantage between X and H? We are representing as A and B. Let me explain to you. These components are basically to show that can distribute melt, but here we have a kind of tighter tolerance when it comes to the vessels could become a little bit weaker, and at also same time, there is a chances of manifold to be kind of becoming weaker as well. But if we go with a H design, considering the steel, which is very, very important for a hot runner to be making it up, the steel makes a very important factor for a hot runner design. If we choose a wrong steel and then polycarbonate reacts to it, and then we have all problems. That's why considering the steel, it's used to contain the distribute melts, for example, it carries the best combination of strength, conductivity, and economics. So economics, we talk about that. The melt volume may be similar between the two. It all depending upon the length, diameter, and thickness. As I explained, equi-channel, equi-distance, equi-diameter, that contributes to making sure that the hot runner design influences very, very important. And finally, we talk about the thermal uniformity here that comes into many of the aspects of that, starting from all the way. We talked about resin uniformity. We talk about barrel and screw uniformity to have the right amount of size of plastic to have the residence time. And then we have sprue heating and then the complete set of manifold right from the top to the front. So these are critical as well. So Husky ensures that our design is catered to the sprue has been heated and the mold flow, whatever is transferred from the machine, it is always maintained and distributed all the way to the front of the mold and to making sure that it doesn't get degraded anywhere. Just to give an example of that, we have a manifold design here with a full perimeter wrap of a single heater and a single thermocouple, of course. In any given circumstances, we can say that there is nothing wrong with respect to this layout of heater profile. Yes, of course. But what we saw, this was in the past, we used to design like that. But exclusively for polycarbonates, we tend to see that there is a kind of a difference between running a temperature of thermal uniformity when it comes to melt channel. When we run the FEA, thermal FEA, have a temperature difference in this case that you're seeing on a simulation is about 37.7 degrees C, an overshoot of 12.8 degrees C, an undershoot of 24.9. This is what we observed. Then we end up to we went to product design and development. We told, how can we improve that? So when we did that, we came up with a very unique design. Of course, you can see there are just each individual drops has been taking over the sequence. That's in this case, we have exactly a total of 5 nozzle manifold heaters dedicated, each one of them. Of course, for the center is different, but the 4 of them. Doing that with the heater optimization on individual zones and thermocouples, we end up coming with the temperature difference of about 10.9 degrees from 37.7, a significant reduction. The overshoot from 12.8, just about 1.6 degrees C itself, and undershoot from 25 to 9.3. This is a fantastic thing that we are designed. So we live with that one too, especially for polycarbonate resin. We see that as that sensitive to when it comes to thermal FEA. Melt degradation. Here we are going to see that the resin is in state elevated temperature. The lower is small, its risk of degradation. We talked about residence time. It's very, very critical to make sure that PC resin is very sensitive to heat and thus residence time as well. So it should not be staying longer time at any point of time. We should clear up whether it's in barrel or in hot runners. So here I talk about the kind of scenario, the causes and effect. I'm going to go with these slides. If you look at these slides, whenever you see that the volume of the resin is less or small in channel diameter, we see that increase in peak pressure. And then what happens is that I or anybody as a process person, he tends to rise up the temperature. Once you rise up the temperature, obviously the melt viscosity changes, easy to flow. And then I go into talking about stability. So when we talk about stability, it's going to go down. Obviously, why? Because I have not chosen a right amount of volume for polycarbonate. In turn, I'm compromising it by increasing the temperature because of the pressure that we are seeing, and eventually stability is compromised as well. So the goal for us to making sure that the final part quality by burning and degrading is eliminated. So in order to do that, we need to make sure that our decreasing temperatures by the kind of a linear approach to having this approach is designing an application would be very good. To having it, the volume of resin here comes up. We have a volume on the right side. Automatically, you see in green, the pressure is coming down. Temperature is going to come down as well. And eventually, the stability is very well maintained. The operating temperature can be decreased, especially when compared to low volume design. All right. Now, I just want to briefly touch base on ultra short. This is something that we want to be proud of to promoting this one, just purely because there are so many components today in the world that it is unable to mold in conventional systems purely because of peak pressure. The smaller the parts, the thinner the parts, the higher the peak pressure. Whenever we have a machine kind of limitations with respect to pressure, it cannot be molded at all. We say, sorry, we don't, no matter what size of screw that we take, excuse me, but Husky is proud to use ultra short, that pressure is incorporated into Husky's hot runners. And from there, we deliver that product whichever cannot be molded on a conventional system. So we have a separate webinars and systems, and also on the YouTube that you can see about ultra shots that going to happen. I don't want to take too much time on this one today, but definitely it's a worth a visit to take and to making sure that why this is so well designed from Husky. And finally, I want to also go here with respect to work cell conditions to having a general notes for troubleshooting. Geometrically balanced manifold and melt channel layout. Manifold melt channel diameter. As I said, it should be pressure capability, material thermal stamina, optimized manifold thermal profile. I did explain to you on the manifold itself. Optimized nozzle thermal profile, appropriate nozzle size. That's the melt channel sizing that we select. If it's like smaller or bigger, we end up with whether it's a less presence, you create pressure, or the larger it's going to have degradation because of residence time. Gate control appropriate for application and requirements. So the defects of troubleshooting that we generally see is that we have consistent streak, intermittent streaks, black specks, and pressure limit is always time and time again we talk about pressure limitations because it is so critical for a PC resin to having these ones. So when it comes to that, it can be intermittent or consistent. So generally a gate streak consistent occurs can be indicator of too much friction or shear at the gate area that you see on the visibility. It's all clear on the outside surface, but if we have a kind of a wrong selection of gate size, we end up with this type of mark that you're seeing on the screen. So we need to make sure that the temperature of the heat is well maintained. That's where the controller comes into picture. Because of the nozzles, it's communicated between controller and mold heats. And we need to review the gate diameter because of shear and review the gate hardware for condition, meaning to say that if there is any leaks or whatever it is, the problems, whatever related to that one. That's very critical for darkened streaks. Then go with black specks. It's pretty straightforward. What does the black specks do? We are having too much of residence time. We have just overcooked this resin for a longer time. And we just left it like that. And eventually when we run the mold, we end up with black specks. So it's all the time we need to ensure that we do not take any time more than 4 minutes of residence time for polycarbonate. That's been a proven thing for us. I think it's an industry standard that it turns its properties to change to having it. So make sure that we do not end up with these ones to black specks with high exposure to time with minimal flow. And then once again, it's pressure limitations. We have to make sure that we have Husky categorizes always into how do we determine pressure. We divide it into 3 parts. We do the air shot for the machine injecting at certain speed. We calculate what would be the pressure of that. We take that note. And when we do the air shot, we need to ensure that the machine nozzle sprue actually matches the hot runner sprue. Why? Because if we have a kind of a smaller hole that comes as a pilot hole from the machine supplier, at any given time, the peak pressure will always go high. That's not the thing that we need to do. Depending on the product, the shape, the volume, the size, how thin, thick is that one, we would have come out with this is the channel minima required, and then either you make it same or probably 1 mm smaller on the machine. That's a very critical point to understand the air shot, and we calculate that pressure, and then we induce the same shot from machine to the hot runner. When we do that, we calculate machine pressure plus hot runner pressure. We know this. And then eventually, what would be the system that for cavity pressure it takes? Because when it comes to pushing the plastic into a very profiled or thinner or longer and very far off places, the pressure keeps on increasing. So we need to make sure that the viscosity of resin is well maintained. So with all these 3 incorporated, that we Husky will work with the mold maker for the design to making sure that these are all well taken care of so that we can have a good product of polycarbonate resin. And then go with ultra melt. This is something not heard in the industry for many people. I just want to brief that. What is ultra melt? We went on to go the product development for many years, understanding what is the thing that it causes the polycarbonate to degrade or to turn yellowish or to change its properties or to turn black flakes. We all ended up doing it is the steel that is contributing for the hot runner system. If we do not select a right steel, and no matter what kind of profile that I'm going to put up on the heaters, we end up with some kind of problems depending on the different type of grade of PC resins. In order to avoid that, Husky came up with a kind of a separate steel that the kind of whenever the plastic is going to flow, the melt channel for this particular steel is not going to stick on the surface. It just washes. So in this way, we need to make sure that the material of the resin is always constantly being out because of that quality. It's not going to attract to the steel and stagnates there over time as it runs. So that is the thing. It's a proven result in the field. We have several manifold designed, developed, and sold, and we have been very successful in the industry. And in fact, we will be given an award at the NPE in May 2024 for this technology that we have developed in the market. So if anybody is going to go to NPE this year in May, we will be proud to see that Husky will be getting this award for that. So please feel free to reach out to our salespeople. What is Ultramelt, especially if you're going to run PC materials? I assure you that you will be happy to take the best choice of our hot runner system. And then on, I just want to tell about all resins are basically corrosion resistant. It's also used for aerospace grade materials, Titan tolerances and fits, resin stagnation, thermal FEA and evaluated design. And this is particularly today we are using exclusively only for polycarbonate and bioresins. Bioresins is very critical. We want to having the nature to be protected. We are going bio, and we have been very successful in that as well to protect our nature. So gentlemen, here I come with the end of the show. My sincere apologies for the initial start of a mix-up. I hope like this presentation, and if you have any kind of questions, or you can always able to reach out to me, and I'm ready to take the hand over to Hafiz for the next one. Thank you very much.
Thank you, Balaji. It's always a pleasure to listening to you and especially on a topic which is so important. I really appreciate people who have while doing registration, people have sent few questions. But let me start with Ritesh Chaudhary. His question is how to control fumes problem in polycarbonate.
Well, as I said to you that basically whenever you are going to inject the plastic, first and foremost thing, I again come back, please excuse me, don't get me wrong. I'm telling that we are emphasizing on the drawing of the resin of polycarbonate. Once we are going to put that one into the feed throat of the resin, and we are if we have a kind of more shear onto the resin when you are going to recover and then eject the plastic, and especially there are two things that you are going to observe on a resin when you are going to shoot. One is fumes, other is the sound that's going. If you have a thud sound, means your resin is not enough dried. If you have fumes, it is kind of overcooked in the barrel. These are the two aspects of that one. In order to overcome that, you have to ensure that your temperature is well maintained and also the resin is well dried.
Thanks, Balaji. A question from while people registered. How does high pressure cause polycarbonate burning? If you could share your thoughts on that.
Thank you very much, Hafiz, for that. Basically, as I said, the degradation happens of a polycarbonate resin is purely because of shear. So if we have a channel diameter, whether it's screw barrel or a hot runner, any kind of thing, if we do not choose the right selection of those ones, we immediately create shear. Once we create shear, it turns to degrade. Once it degrades, it's going to have a kind of polycarbonate to burn. And you will see that burn mark. It can be seen on the complete surface of the product, or you can be only seeing on the gate. If you recall my presentation slide respect to the gate, if our channel sizing of the gate is smaller, for example, if you want to design X and we didn't do that, we have gone smaller, we are especially creating shear there. That causes burning. I hope I have answered the question on these ones.
Balaji, you have to wait because there are multiple questions. The second question is clear PC more sensitive to injection molding differences than PC with colorant?
It's a very good question. Thank you very much for that. See, PC polycarbonate resin itself, whether it is clear polycarbonate or it's a colorant polycarbonate, it's not going to have any kind of difference. It's the same. It's just that if a clear polycarbonate, if you are going to have a kind of an issue, it's going to be seen visibly. But if you're going to use a colorant, you may not be able to see it, but that kind of problem still persists. And most importantly, we end up with structural defects. So in short, both PC, clear, and color, both will degrade in a situation if you're going to having it and sensitive to injection. So both are same. No changes on that.
Okay. The next one, is it possible to mold PP in PC mold?
Well, first and foremost thing, the thing that polycarbonate is going to, you're asking me whether a PP can be molded on a screw of PC.
PC mold, yeah.
Polycarbonate will run of its thing because you need to know that polycarbonate setting temperatures and running temperatures is about 290 degrees to 300 degrees, I told you. So the shrinkage factor for polycarbonate design is totally different from the poly PP itself. So you can run PP on the same thing, but in order to make sure that the colorants that is being in the screw barrel, all the stickiness of the polyethylene, everything has to be made sure that it's clear. Then you can able to introduce polycarbonate and other if you are running on the same machine.
The next one is how to minimize the amount of black specks when running recycle material.
First and foremost thing, it's a very tricky question to answer for me. The recycle concept itself, we need to make sure that we are doing it in a right way. Recycling is not something that we can able to just pass. We need to have a controlled atmosphere that time and time again it can able to be recycled, and there is a process that can be followed. Otherwise, if we do not follow the recycle process properly, we end up with, again, the density of the resin will be different with virgin versus recycled. And multiple times you're going to then it again multiplies. So in a way, we talk about, or anybody in the industry will always prefer to having it virgin as possible in order to have recycled. I can say that it has to be the responsibility of the stakeholder, molder in this case, to making sure that it is well taken care of with respect to recycling. That comes with, again, proper drying, proper maintenance of mold, barrels, and all those things.
Okay, thank you. We have question from Ratnakar asking, with respect to high gloss injection molded plus, do you recommend something technology from your side which difference it from traditional hot runner systems?
Yes, of course. As I said to you today, for a high gloss product of polycarbonate resin, I showed you this just a few slides back. We call it as Ultramel. We are very proud to have this system to be used for any kind of resin, to be making sure that the clarity of the product will be maintained, and then to making sure that it runs for a longer time without kind of any problems. Of course, all we have to do is to follow the procedures of the residence time, the right amount volume of plastic being pushed through, the hot runner residence time, and the volume is correct, and the mold design and cooling is perfect. With all these things, Husky is very happy to give Ultramelt hot runner system the best solution for that, along with the controller. Yes, it is possible.
We have a CEO from Enlightened Thoughts. He's asking impact on environment and air quality. If you can highlight, share your thoughts on that.
My apologies. I am not in a position to answer. This is a kind of a commercial question for me. I would rather get back to the gentleman if you can able to give the context
Sure.
with our people and come to you. Sorry about that.
And while the questions keep coming, Balaji, the next, if I can ask you, we should PC with the FR, we should make resin channel big or smaller.
Of course, polycarbonate is flame retardant should be in a general term, the PC resin itself, the channel sizing should be larger, but not too large or too small, but just enough. With flame retardant, Husky can able to work with resins or whatever the grade that is being given to ensure that we supply the right amount, and we also recommend the screw size and the barrel size for these ones. We can work with the stakeholders on that.
Okay.
It can be molded with flame retardant.
Sure, sure. We have another question from Anil Kumar. It's asking if you use same mold for PC and PP, how to solve shrinkage and other defects? Is it possible to use same mold for PP and PC?
No, this is something that mold maker has to confirm, because as I told you, the stability of the shrinkage depends on the resin. The shrinkage factor is given by the resin supplier. So based on that, the tool is designed. So any tool that is designed is from the designer perspective, how much shrinkage factor is considered, whether it's polypropylene, ABS, whatever the resin that's going to run. So you will not be able to make the choice for me to say that, yes, it can be run. We have to go back to the mold maker and the designer and what kind of shrinkage factor has been introduced for the inserts. I will not be able to answer that question for this particular case.
Okay. Balaji, while we have more question, but I would I have a we should end this, and I will send all the question to you. You can reply directly via mail. And on behalf of manufacturing today, ITP Media, I would say a big thank you to you for sharing your thoughts and giving your knowledge to us. And I also want to thank the audience, because this by far number of questions which are coming, and your attention for this subject. I'm sure we can do another series on this. Thank you, Balaji. Thank you very much for sharing your experience, and we really appreciate and commitment for sharing your insights. We hope it was a learning experience for everyone. We'll come back with the entire video on our website on manufacturingtodayindia.com. Till then, thank you very much. Stay blessed. Stay safe.
Thank you so much, everyone, for joining. Really appreciate it. Thank you so much. Good day to you.